There's already some airports in the US who actually have to deload a bit the aircraft weight passengers because we cannot take off. Also, the rise of sea level can put some airports in danger. There's a lot of effects of climate change on aviation also. Without available green hydrogen out there, people won't be buying our systems. What sets us apart is that we have an aerospace DNA. We have a mix of expertise of hydrogen engineers and aerospace engineers. We actually help our customers from end to end. So I would encourage people to go deep into hydrogen sector because I think he has a very good future.
Ladies and gentlemen, welcome to another podcast episode here at Realize Live in Amsterdam 2025. Today I have a very special guest, Enric. Welcome to the show. Maybe you can give us a little bit of an introduction, like who are you in the first place and what do you do at H3 Dynamics and what is actually the background of H3 Dynamics?
Yes, of course. Present myself. My name is Enric Royo Jiménez. I'm an aerospace engineer background and I'm working at H3 for 5 years. Now I'm responsible of aviation program and digital simulation at H3 Dynamics. So at H3 Dynamics, what we do is our goal is to be a leader in the decarbonization of the aviation industry. Mm-hmm. We design and manufacture hydrogen systems for the aviation industry to decarbonize commercial aviation and also for the defense sector and to maximize the endurance of drones, for example. So that's our ultimate goal, and we have different products in our portfolio. We have the division of hydrogen power generation with fuel cells. And actually, we have fuel cells for drones and for aviation, so ranging from a few watts to 400, 500 kilowatts. So fuel cells that are really specific for aviation. We are an aerospace company, so we design with an aviation mentality. So all our systems are very lightweight and compact for aviation, following the most strict standards out there. So that's I would say that's the power generation side for airborne systems, but also for ground systems, where it's easier to start in terms of certification because today there's not a really standard regulatory framework for hydrogen in aviation. So it's easier to start out with ground operations, with ground power units, and then move on towards airborne systems. So that's on the power generation side. And then we realized that without available green hydrogen out there, people won't be buying our systems. So we're actually also producing and selling electrolyzers and hydrogen refueling units to have hydrogen available on site for our customers, green hydrogen from electrolysis. So it's like the chicken and egg, because if without hydrogen, people won't buy our fuel cell systems, but without fuel cell systems, people won't want to move towards the hydrogen industry and infrastructure. So we support our customers in those axes. So we want to move towards have the industry move towards a hydrogen based sector, and we do this with an aerospace mentality. So what sets us apart is that we have an aerospace DNA. I would say we have a mix of expertise of hydrogen engineers and aerospace engineers. Mm-hmm. And we actually help our customers from end to end. For the testing, for the certification, for the design, and we use all our knowledge to try to make the most safe, lightweight, and compact systems out there. So maybe you asked a bit of the background of H3. It all started in Singapore, founded in 2015 by some French entrepreneurs in Singapore. We started with small fuel cells. So we had a lot of experience already in hydrogen systems for other industries, but we tried to put all this knowledge towards the aviation industry, so make them very lightweight, very compact. And we started with drones. We have a drone assembly line in the US, in Austin, Texas. But then in 2017, the company founded in France, the Aerospace R&D Center in Toulouse, actually, next to all the aerospace companies there. So it's quite strategical for us. And there we started to develop and design our fuel cell systems for aviation, which are slightly different than the ones we use for drones, up to 400 kilowatts. So the systems that are already available there with a high TRL, so TRL 9, which we will keep improving and keep reducing the weight today. So one of our main customers the last few years was Airbus. We delivered a 500 kilowatt fuel cell system for an auxiliary power unit of an A330. That means that we're moving in the good direction. So we need to keep improving. Our plan is to double the specific power of our systems towards 7 kilowatt kilo in the future, in the next 3 years. And to do that, the company will invest in the next 3 years more than 25 million euro in France to recruit more than 100 people by 2027. We'll be moving the headquarters of H3 Dynamics to France also. So this is part of a first step of more than 150 million investment in R&D and in manufacturing facilities in Toulouse, where we think the future of aviation is there. So that shows that the company is investing in France in the future of aviation. So yeah, that's more or less a summary of what we do at H3 Dynamics. So yeah, fuel cell systems for aviation with an aerospace mentality, and with also application for defense.
Talk a little bit about the topic of decarbonization. Why is it so important now and in the coming years?
Yeah, maybe I can take a step back on that and say, why do we need to decarbonize the aviation industry? How do we pollute today as an industry? So talking about in-flight emissions, as any other combustion engine, we use hydrocarbon, so kerosene, which mixes with air, and this produces in a combustion some CO2 and some water vapor plus heat. But also, not any combustion is perfect. So there's some particles that we call soot that are released also from the engine. And finally, there's also some NOx created because there's actually the very high temperatures in the aircraft engine, which makes that the nitrogen and the oxygen inside the air mix together, form this NOx. So all of these byproducts, not all of them, but many of them are greenhouse gases, especially CO2. And NOx is actually an indirect greenhouse gas because it helps formation of ozone in the low stratosphere. And then there's also the water vapor, which is a natural greenhouse gas in the world today, which actually traps some heat. And the fact that we are creating more CO2 that heats up even more the atmosphere means that the atmosphere can take more water vapor because a more hot environment takes more water vapor. So it's actually a loop that goes on and on and on. And finally, the other aspect is the contrail formation that we talk a lot about. So actually the soot from the incomplete combustion mixed with the water vapor and the cold atmosphere outside creates this contrail. It's like when it's cold outside and you exhale, and you see that small that white cloud. So that's the contrail actually, and that also contributes to global warming. And actually, it's more on the contrail side than on the CO2 side. It's actually I think 60% and 70% and 30% formation. So 60% on the contrails and 30% on the CO2. So that's how aviation in-flight pollutes today. I don't know if you know how much aviation represents in as an industry in the pollution and the greenhouse gases today.
No
percentage. It's around 3-4%.
Okay.
Maritime is 3% also. Train is 1%. But for example, all the cars and all the what we call road is 16%. So it's not one of the most polluting industries, but we have to work towards a net zero aviation industry. Also, not just because of the heating up of the climate, but also because actually climate change also impacts aviation, because a hotter atmosphere degrades the engine's performance and creates less lift on the aircraft. So actually, there's already some airports in the US where we actually have to deload a bit the aircraft weight, the passengers, because we cannot take off. Also, the rise of sea level can put some airports in danger. So there's a lot of effects of climate change on aviation also. So that's a double interest for us to decarbonize the industry. And why do we go towards hydrogen? So that was your initial question. Sorry for my short
good background.
Yeah. So basically, there's several ways of decarbonizing. First of all, we at H3 Dynamics we think there's three axes. The first one is efficiency. So making aircraft more efficient means you do the same thing but with less fuel. So that's the first axis. Actually, aviation has been trying to be more efficient in the last 50 years. It's been 40% more efficient. Has 40% more efficient aircraft than 50 years ago. The second axis is instead of using a fossil fuel, use a green or decarbonized fuel, like hydrogen. For example, there's two ways. Either you power the aircraft electrically, so via a motor that turns a propeller, or you use combustion. To power it electrically, you can use batteries, or you can use hydrogen fuel cells like we do at H3 Dynamics, which convert hydrogen into electricity. And combustion-wise, you can use hydrogen to do combustion with oxygen also, and you can use also sustainable aviation fuels that come from feedstock, or also from hydrogen plus the capture of CO2 in the atmosphere. So in all of these four options that I said, hydrogen is in three of those. So hydrogen is actually one of the main fuels that will be help decarbonizing the industry. So that's the second topic, using a fuel that has not a CO2 impact. And finally, the third point is some moderation, because as I said before, aviation is more and more efficient with the years. What does that mean? Actually, is that a company, an airline that is more efficient, can reduce the prices of their tickets because they're burning less fuel. That means that people buy more tickets because tickets are lower cost. So that makes what we call the rebound effect in aviation. So the more efficient we are, the more people fly. So obviously there needs to be also some type of moderation in our flights.
So that was very well explained, Eric. Thank you so much. I'm wondering, from a simulation standpoint, or maybe take another step, or the next step into simulation, how do you actually make sure that you can accurately simulate these fuel cells you talked about?
Exactly. So that's a good question, because the advantage of having a good model of our systems is that we can actually avoid doing some physical tests in the future, because tests are expensive, they're time consuming. So doing a test in the computer, avoid doing it physically, accelerates your R&D a lot and minimizes your costs. But you need to have a very reliable model to do that, because we're working on aviation. We need to have a good representation of our models, and to do that we need some data. So we need physical data to validate our models. So at H3 Dynamics we have access to lots of data in different conditions, temperatures, pressures, environments, etc. From our testing, and from our clients, which we feed into our models, our own models created by us using Siemens software. And then when we actually compare the experimental results to our digital simulations, we try to fine-tune some parameters to make it really reliable and robust. And once we have an accurate model like we have today, we can say we're top in the world in this. We have an accuracy of less than 3% relative error compared to our experimental data, which is very good. So once you have this, you can avoid doing future tests and just use your simulation tools, which we use today is Siemens Amsync for 1D and FlowFD and StarCCM for 3D modeling.
Got it. So basically what you actually do at the end of the day is building a digital twin or using a digital twin. And maybe it's very important for the audience, because there's a lot of misconceptions maybe about the word digital twin or digital model. Maybe you can quickly explain, like, what does it actually mean in your terms? What is a digital twin?
So ultimately, what we want to do is to reach a digital twin. But what we have today, I would say, is actually a digital model. So a digital model is, at the end, is a digital representation of a system. In our case, a fuel cell system. So we have a model in our computer that simulates the behavior and predicts the behavior of a physical system we have in the lab. And from there towards a digital twin, in our understanding at H3 Dynamics, there's different definitions for a digital twin. But digital twin is actually a twin. So it's something that is simulating and representing something live that's on an aircraft. So we would be in our computer monitoring and seeing how the fuel cell system on our aircraft is evolving in real time without needing to be on the aircraft itself. So moving towards a digital twin in the industry is very useful, because we can predict component failures. So we can move towards a predictive maintenance approach, which is very important for aviation industry, operational reliability. And also we can predict the aging of our components, degradation models, etc. So that's more or less the difference between a digital model and a digital twin. But today it gets mixed up very easily. Yeah.
Absolutely. I'm wondering then, if you talk about a digital twin, and you said you almost or don't have to do any testing at all. So how do you actually use the digital twin models on a daily basis? Like, what do you actually monitor? You talked about predictive maintenance. What are some of the key parameters that you look at when you talk about a hydrogen fuel cell?
So digital twins, digital models, we use them today both internally on our R&D and externally for our clients. Internally, we use them to make architecture trade-offs. Basically, design when we're doing a new system, designing a new fuel cell or a new fuel cell system. What we're actually doing is we're using the model itself to actually change some components or change some parameters in some components to see what is the best component we can put here, or what is the best architecture we can do. And actually, this is how we use the systems today to make these trade-offs internally. And externally for our clients, having a digital representation of their models is very important, because actually when they buy one of our systems, hardware, so physical system, they also buy the software part. So we send them a black box of our system. They don't know what's inside for IP reasons, but actually they can put this black box in their power plant or powertrain or aircraft system simulation. And actually, they can actually predict what the performance of our system is before actually doing a flight test, which is very expensive. Or actually, they can work on the control of their powertrain without needing to actually test the system today. And you asked about the parameters we look into when modeling fuel cell systems. So both on the hydrogen side and the air side that goes into the fuel cell system, we look into pressure, temperature, mass flow, humidity. So we have all these types of sensors in our test bench to feed into our models, which we then compare to the results we have in AmSim to validate our results.
Do you feel that there's some misconceptions in the industry about hydrogen fuel cells still today?
Well, hydrogen fuel cells have been there for a long time already. Actually, the automotive industry has been using them for some time. I don't think that there's misconceptions or not on the hydrogen fuel cell stuff. Maybe on the hydrogen side, yes, because maybe we have in mind that safety-wise, it's not the best fuel.
Yeah.
But actually, it's not like that. What we have today are systems that are really reliable, really safe. Hydrogen obviously is a combustible fuel, which you have to take care with when operating. But the systems we design today have all the safety measures, have all the precautions when using hydrogen, maybe what that was not done in the past. Also, the gas you put in your car is flammable. So technology is evolving. Hydrogen technology is evolving at a very fast pace, and aviation industry needs a very safe and reliable hydrogen system. So we're working at H3 Dynamics in reducing the weight of our systems, but at the same time increasing the safety of a system. Sometimes when you want to increase the safety of a systems, you add valves, you add redundancy, you add weight. Well, so what we want to do is increase the safety of the systems, but also reduce the weight. So that's what's challenging, and that's what we do at H3 Dynamics, and that's what's a game changer for the industry.
Yeah, super interesting. You talked a little bit about decarbonization earlier on, so I'm wondering, from your perspective, there's a lot of upsides, but there's probably also some downsides when it comes to hydrogen fuel cells. So what are some of the downsides? And how do you tackle them, maybe?
Yes, exactly. So at H3, we want to maximize the advantages of using hydrogen. As I said, the hydrogen has more energy per kilogram than kerosene, for example, today. So the same mass of fuel gives you 3 times more energy than the kerosene today. So that's a really good advantage. And if this hydrogen is green, then it's zero emissions. No, not zero emissions, but very low emissions.
Yeah.
So those are the advantages, but also there's some challenges with hydrogen. As I mentioned, regulation. So there is no regulation. So you want to really put a hydrogen fuel cell in the aircraft today. It's difficult, but because there's no framework around it today. So we're working on that. One of the main challenges of hydrogen is its energy density, because actually, as I said, 1 kilogram of a mass of hydrogen is better than 1 kilogram of kerosene, but 1 liter of hydrogen has less energy than 1 liter of kerosene. So actually, we want to replace on an aircraft today, retrofit hydrogen and put the same amount of energy in terms of volume. We have to remove some passengers because they wouldn't fit. Yeah. So we're working, so the industry is working on compressed hydrogen gas. You can store it as a gas. So you want to compress it to minimize the volume. You can store it in liquid form, so that's even better than in gas form in terms of volume, but you have to be at cryogenic temperature, so at minus 253 degrees. So that's a challenge also. And at H3, we're working also on solid state technologies, so metal hydrides to store hydrogen in a more, I would say, standard pressure, standard temperature, so increased safety of our system. So those are the three axes of hydrogen storage today. But it's still a challenge to put hydrogen in an aircraft in terms of the volume. And the last point is in terms of specific power of the fuel cells themselves. So at H3 Dynamics, we have systems that are very light today. And as you know, every kilogram on an aircraft counts. So you want to make the systems as light as possible. So our fuel cells today are very light, but we plan to double on the specific power of our systems in the next few years, the next 3 years. Because aviation needs 1.5 kilowatt kilo fuel cell system to be feasible today.
What excites you the most about hydrogen fuel cells for the next 5 to 10 years?
A good question. Personally, as an engineer, fuel cells are amazing. So my background is in aerospace engineering, but I've been working with fuel cells for more than 5 years now, and they are amazing. They integrate different domains. They have electrochemistry for the reaction. They have fluid mechanics. They have thermodynamics because you have to dissipate all the heat it produces. You have electricity. You have structures because you have to have a good system that takes all the accelerations. So it makes lots of physical domains, which is very interesting for engineers. And on the decarbonization side, it's positive. Personally, I love the aviation industry. So I joined H3 because I think that using fuel cells for aviation is one step further towards decarbonization of the industry.
Mm-hmm. I think that's very, very cool. So Enric mentioned earlier on the topic of predictive maintenance. So we have to talk about AI or machine learning, how some people call it. So how do you see AI playing a role in this whole fuel cell development?
Mm-hmm. So AI today is one of the key topics out there all the time, but we just don't want to put AI like that on our systems. We're working on it, as I mentioned, working towards a digital twin perspective of our digital models. And AI can be really useful for us when it comes to using our models for predictive maintenance and for degradation of our fuel cell systems, our components, and checking for component failures. So actually, we would use in the future AI to feed. In fact, we'll use lots of data to feed our models and use AI and machine learning to try to make the most accurate predictions of our fuel cell degradation. And as I mentioned in my previous answer, that fuel cells are a complex mechanism with many different physics around it. So using AI to help us model these systems is very useful. But you need a huge amount of data to do that. So we are collecting all this data from different tests we do on different clients. We will, in the future, we'll feed this in to all our models and use AI to create the most reliable and robust aging degradation models.
So we think about the future of aviation, Enric. I'm thinking, will there be a hybrid solution where you basically have hydrogen and another fuel storage or system that you want to use, or do you think it's solely hydrogen-based?
I think that aviation, hydrogen will play a key role in the future of flights, but there will be other systems powering an aircraft. I think for small, very small aircraft, battery can be enough. Battery electric, so just having electricity through a battery. For more regional and medium-long range, fuel cells I think will be the key player there. But for long-haul, long-range fuel cells don't have the specific power to perform those flights. So we will need to be using combustion, I think. So using hydrogen combustion or SAF. And both of them would require hydrogen at the end. So hydrogen is actually a key role, but in different forms, I would say.
So a lot of people who are watching this podcast, Enric, are maybe in the beginning stage or like still studying in university, and they want to tap into this field, this fascinating field of fuel cells with hydrogen systems. How do you advise them to get started? Well,
I would say join H3 Dynamics as a first
obviously.
But But yeah, how you can start on fuel cells? As I said, fuel cells is not just there for aviation. It can be used in automotive, and hydrogen as an energy vector can be used in many things. Storing energy from renewable energy that we have, and hydrogen is a very important aspect. So hydrogen. Studying hydrogen today, so I would encourage people to go deep into hydrogen sector, because I think it has a very good future. It will play a key role in decarbonizing of the aviation industry, but not just that, on the energy sector itself. And in terms of hydrogen fuel cells, I'd say it's just an amazing component. I got fascinated by it 5 years ago. I'm still working on it, and as I said, mixing lots of multi-physics domains. So any engineer that is passionate about integrating different physics together, a fuel cell is definitely a must to see.
Super. Thank you so much, Enric. So you heard it from Enric himself. If you want to learn more about H3 Dynamics, we're going to put all the relevant links in the description so you can check it out. And if people have any questions, they can probably reach out to you or H3 Dynamics.
Yes, of course. Thank you, Jose. Thank you very much.
So that's a wrap. This was another episode of the Realize Life podcast here in Amsterdam. I hope you enjoyed it. If you want more information, I share all relevant links with you in the description. Make sure to follow, hit the like button, and also make sure to follow SimCenter for more information about the world of simulation, AI, and engineering.